Swayam Prabha. Digital India. Educated India.
Good afternoon and welcome back to lecture number 14, part 1 on the topic refrigerant. This is the first topic in the third module. In this one, we will be studying about the refrigerant, what is the function of a refrigerant, how it is classified, properties of refrigerant, what is the environmental impact because of the use of some refrigerants, etc. So, a refrigerant, it is a substance or a working fluid which is employed in a refrigeration and air conditioning system. Can be a single substance or a mixture of two substances, that is blend, refrigerant blend. It takes the heat from the low pressure or the low temperature region and reject it to at the higher pressure. The heat which is removed at the lower pressure region is thrown to the higher pressure region where it is rejected, and during this process the refrigerant undergoes phase change in the evaporator from liquid to vapor and in the condenser from vapor to liquid. So it absorbs heat at low pressure and rejects at high pressure, which while undergoing phase change in the evaporator and condenser. So before seeing the classification of refrigerant, let us see the history of refrigerants. So in 1874, sulfur dioxide was used as refrigerant for the first time. Then in the next year, ammonia has been used, and of course it is an environment friendly refrigerant, natural refrigerant. In the year 1878, methyl chloride the refrigerant has been discovered and it has been used. CO2, carbon dioxide, in 1881. In the year if you see the era up to 1900 or so, the refrigerants which were used are natural refrigerants. The man-made or artificial refrigerant R21, that was invented in 1928, and from 1931 the commercial production, mass level production, and also for the commercial purposes. So that was commenced from the year 1930-31. So that is R11 and R12, where this company DuPont. So they were the leaders of the manufacturing of freon-based refrigerants. Broadly, the refrigerants are classified into primary and secondary. Primary refrigerant is the one which is used directly in the system. Whereas secondary refrigerant, it is used to transport the energy. Like in case of a system which is a refrigerant which is used directly in the system, like the vapor compression refrigeration cycle or the air conditioning one, the one which is used in the air conditioners and the refrigerator. So where the refrigerant, the working fluid, undergoes a phase change in both the evaporator as well as in the condenser. Whereas the secondary refrigerant does not undergo phase change. Examples, there are a lot of examples for the primary refrigerant: R11, R12, R21, R134A, R123, 407, R410, etc. R7 and natural refrigerants, carbon dioxide, ammonia, water. Secondary refrigerant, if you say, will normally the refrigerant which is the, when we say secondary refrigerant, the refrigerant cools a medium. It could be water, and for sub-zero or negative temperature applications, brine will be used, since water will freeze at 0 degrees centigrade. So brine, like ethylene glycol, calcium chloride will be used. That will be cooled. That secondary fluid will be used to cool the air. The heat transfer is from between the refrigerant and the water or the brine, then from water or brine to the air. So that is how. So the refrigerant is not directly cooling the air. It is not directly cooling the air. Whereas in the primary refrigerant, it directly cools the medium. This is the broad, classification of the refrigerants. So again, it is divided into two categories: pure fluid, that is a single substance, and a mixture, combination of two or more than two. So under pure fluid, we have got synthetic. So that is the refrigerants which were made by human beings, artificially made. Under that, CFC, chlorofluorocarbon, HCFC, hydrochlorofluorocarbon, HFC, and HFO. So under CFC, we have got R11, R12, HCFC, R22, R123, HFC, R134A. We have used this refrigerant, especially when we are solving the numerical questions pertaining to the ideal vapor compression refrigeration cycle under various operating conditions. Then we have got R404A, then HFO, that is olefins based, this one, HFO1234YF, HFO1234ZE. When it comes to natural refrigerant, there are two subcategories are there. One is organic, that is hydrocarbon based refrigerants, propane, butane, etc. C3H8 is propane, C4H10 is butane. When it comes to inorganic refrigerants, ammonia is there. R717 is ammonia. Molecular weight of ammonia is 17. Water is 18. So R718 is water. Then we have got air, carbon dioxide. Under mixture category, we have got azeotropic mixture and zeotropic mixture. So I will be explaining about the difference between these two mixtures in the subsequent slide. R500 series, that is R500, 502, 503 comes under azeotropic mixture, and R400 series, 404A, 407C, 410A. If you take azeotropic mixture or zeotropic mixture, it is not a single substance or a pure fluid. It is a combination of two or more substances. So azeotropic mixture, it is a mixture of usually two substances which behaves as if it's like a pure fluid. So it behaves like a single refrigerant, though it is a combination of two or more substances when condensing or evaporating. That is, the temperature remains constant at a given pressure. That is isothermal process. Examples, like if you see the previous slide, I have mentioned about R500, R502, R500, 502 and 503, and under zeotropic 404, 407, 410. So let us see the composition of these mixtures. R500 is about 74% R12 and 26% R152. R502, this is R22 and 51.2% R115. That is around 49% R22 and 51% R115. Then R503 is about 40% R23 and the remaining is R13. Zeotropic mixture is a mixture whose composition in liquid phase differs from vapor. So zeotropic is mixture composition in liquid phase and the vapor phase differs from each other. So therefore, these type of refrigerant do not boil at constant temperature, unlike azeotropic refrigerant. Examples are 404A, 407C. Here there is it's a combination of three refrigerants. One is R125, 44%, R143A 52% and the remaining 4% is tetrafluoroethane, that is R134A. When it comes to R407C, it is a combination of 23% R32, R125 25% and the remaining 52% is R134A. R410A refrigerant zeotropic, it's a combination of equal amount of R32 and R125. Selection of refrigerant based on properties such as thermophysical properties, thermodynamic properties, environmental and safety properties, chemical properties, and economic properties. Before seeing the selection of refrigerant, the COP of a system depends upon the operating temperature limit, number one. Second thing, if you take the system design, size, the cost involved, like operating cost, maintenance, serviceability, etc. All these things depends upon the choice of refrigerant that has been selected. Refrigerants are selected based on these four properties: thermophysical properties, environmental and safety properties, chemical properties, and economic properties. So let us see the properties, thermophysical properties. First, under thermophysical properties, these are all very important properties. The first one is high evaporator pressure, and second one is low condenser pressure. Let us see here. Evaporator pressure high and condenser pressure is low. Or let me write high and low. Pressure ratio is the ratio of pressure ratio or compression ratio is the ratio of condenser pressure to evaporator pressure. So that is discharge by suction. Now, if I have high pressure evaporator pressure, that means the denominator is more. If denominator is more, if P is high, then pressure ratio will be less. The denominator is high. If condenser pressure is less, that is the numerator, then also pressure ratio will be less. So the numerator is less, ratio becomes less. Denominator is more, the ratio is less. So when we have a low pressure ratio, the volumetric efficiency will be better, will be high, which will lead to low power consumption by the compressor. If the pressure ratio is less, volumetric efficiency will be more, and the power required to drive the compressor also will be, power consumption will come down. On the other hand, if we have low evaporator pressure or high condenser pressure, then the pressure ratio will change. High condenser pressure, when we have a high condenser pressure, then the materials, the thickness of the tube that will be used for the design and construction of condenser, we cannot use a lightweight materials. So the cost, the material, the cost involved, the thickness of the material also will increase when we have if you have a high condensing pressure. Latent heat of vaporization, that should be, it's a very important property. It is desirable to have a high latent heat of evaporation. Specific heat, it should be low for liquid and high for vapor. And one more thing, if the evaporator pressure is high, the compressor size will be small for for the quantity of mass flow rate that has been circulated. Because the specific volume will come down. Or in other words, the density will be more. Cp specific heat capacity is Cp. Cp of liquid should be low and Cp of vapor is high. Low for liquid and high for vapor. When we have a low specific heat capacity value, so the degree of subcooling will be large. Degree of subcooling increases. High Cp value of vapor will have degree of superheat small. Degree of superheat will be small. Okay, so this is high, this is small. Okay, so that is the advantage of this one. Because of this reason, it is decided to have a low specific heat value for liquid and high specific heat value for vapor. Suppose if the degree of superheat is more, that means if the Cp of vapor is small, then the degree of, suppose if the degree of superheat is high, then the suction temperature will increase. And the suction temperature will increase, then the density will come down. If the density is less, then the specific volume will be more. Then the compressor size will, the compressor required to handle that mass flow rate of the fluid that will be circulated, it will be large. We cannot have a compact size compressor. Thermal conductivity. So, thermal conductivity is represented by the letter K. It should be high. In order to have high should be high, so that heat transfer coefficient is K value for both liquid and vapor need to be high, so that the heat transfer coefficient is high. Okay, viscosity to be low. If the viscosity is low, the pressure drop will be less. Small pressure drop. Then boiling point, freezing point. Boiling point to be low and freezing point to be low. If we take the natural refrigerant, water, its boiling point is 100 degrees centigrade and the freezing point is 0 degrees centigrade at atmospheric condition, that is 1 bar. If we compare this boiling and freezing point with ammonia, whose boiling point is minus 33 degrees centigrade and freezing point is minus 77 degrees centigrade at atmospheric pressure of 1 bar. So to summarize this, so the evaporator pressure to be high, condenser pressure to be small, low condenser pressure, so that the pressure ratio is less. The pressure ratio is less, the volumetric efficiency is better, and the power required to drive the compressor is less. Latent heat of vaporization should be high for the refrigerant. Generally, refrigerants with low molecular weight have high latent heat of vaporization. Refrigerants that has lower molecular weight has high latent heat of vaporization, high latent heat of vaporization. So before going to the next slide, let me write the symbols which I have used here so that it will be easy for the students for reference. Cp is specific heat capacity. Specific heat capacity. K is thermal conductivity. L is liquid. This is symbols. And V is vapor. Let us move to the next property, environmental and safety properties. We don't want the refrigerant to be a flammable one, so it should be a non-flammable, non-toxic, non-corrosive. It should not react with any materials. Very important property, the next one. It should zero ODP, ozone depleting potential, and low GWP. If not GWP also, negligible GWP. And it is based on, selection is also based on the total equivalent warming impact. This ozone depleting potential. What is this ozone depleting potential? So there is a layer in the stratosphere, that is this ozone layer, which protects the Earth's surface from harmful ultraviolet radiation. Otherwise, what will happen if the UV radiations are allowed to pass through the Earth's surface? It causes a lot of diseases on the humans. So what happens? This ozone layer is getting depleted, thinning of the ozone layer. This is due to human activities, like due to release of some chemicals, CFC based refrigerants. These things, they break the ozone molecules, and thereby it destroys the ozone layer, depletes the ozone layer. So next is global warming potential, that is warming of the Earth's surface due to the presence of greenhouse gases such as carbon dioxide, methane, nitrous oxide, etc. So more than the thermodynamic properties, the refrigerants should not make any impact on the environment. Of course, thermodynamic properties are also very, very, very important, but especially these two, environmental degradation, that is the warming up of the Earth's surface, that is the global warming, where temperature rises there due to the increase in the presence of greenhouse gas emissions. Then the depletion of the ozone layer. Chemical properties should not react. It should be stable throughout the cycle. It should mix well with the lubricating oil. Some of the refrigerants are miscible, some of them are immiscible with lubricating oil. And it should be easily, if there is any leakage, it should be easily detected. For example, if there is a release ammonia refrigerant from the system, due to its odor, the pungent smell, it can be easily detected. But however, that depends upon the concentration level of ammonia present, that is released in the atmosphere. That is, if it goes beyond a particular ppm, parts per million, then it causes irritation to eyes, etc. Economic properties. The refrigerant should be easily available, and it should be cheap. If you compare the cost of 1 kg of ammonia with 1 kg of R134A, tetrafluoroethane, it is significantly, R134A is very, very costly, very, very costly compared to ammonia. And ammonia is a which is produced naturally, so it is easily available. So let us make a comparison. Let us make a comparison of the refrigerant properties. So the first three refrigerants are, first three and the last one are natural refrigerant. So this is air, second one is carbon dioxide, R717 is ammonia, then R12 and R11 are there, then R718, that is water. So the boiling point of ammonia is say -33 and the freezing point is around -78. Water, all of us know the boiling point and the freezing point of water. R11 is 23.8 minus 111 freezing point. R12 minus around -30 minus 158. Carbon dioxide minus 78.4 and minus 56.6. Just to here I have compared the property of two CFC based refrigerant, that is chlorofluorocarbon based refrigerant, with that of four natural refrigerant, that is CO2, water, ammonia, water and air. Next table gives a insight on the property comparison based on the ozone depleting potential value and GWP value. So here you can see this is a natural refrigerant. ODP is 0 for ammonia and water. GWP is also 0. Hydrocarbon refrigerant is also ODP is 0 and GWP is negligible, very, very small value. Whereas if you see CFC, for CFC the ODP is 1 and GWP is HCFC category of refrigerants have very, compared to CFC, the ODP is less, and when compared to R12, R22 has got less ODP, and this one, even the GWP is also much lower. So I will stop this lecture at this point. We will be continuing in the next lecture.